In part 3 of this video series on assembly programming for the PIC16F1719 microcontroller, we will introduce some logical commands. The PIC16F1719 allows us within assembly to perform various logical operations such as ANDing, ORing, and exclusive ORing. So let's begin by introducing some of these commands. The first command to introduce is ANDLW. That performs a bitwise ANDing of a literal value with the value in W. And what that means is it will take the most significant bit in W and the most significant bit in whatever literal that you specify and put those two bits through an AND gate. And whatever result would come out would be in the result there, and you can specify that this will actually put the result into W. And so if you said ANDLW 0x0F, then you know that the most significant 4 bits of the result would go to 0, and then the least significant 4 bits would be the same as whatever the least significant 4 bits already were in the W register. And that showcases that this is really useful for what is known as bit masking, which is where you might only be interested in a few of the bits in a register, and you don't want to have other bits that are unimportant modifying your logic. And so in this case, you can keep certain bits and clear out others. So doing an ANDLW 0x0F would clear out the upper 4 bits and maintain the lower 4 bits. You can do an OR with IORLW, and the I specifies that this is an inclusive OR, what a lot of people refer to as a traditional OR, regular OR gate, and that is to distinguish it from the exclusive OR, which we will talk about shortly. So this does a bitwise ORing. This is a useful way to do multiple bit sets at once. So if you wanted to set several bits, rather than doing bit set F, bit set F, bit set F, any of the places where you put a 1 in the literal value will be set into those particular bits in the W register. So if you did IORLW 0x0F, that would set all of the lower 4 bits while maintaining what was in the upper 4 bits of W. XORLW is the exclusive OR, and so that is very similar to the inclusive OR, except if both of those bits are 1, it will output a 0. And so this is useful for toggling bits. So if a bit is a 0 and you have a 1 in the literal value in that position, it will toggle to a 1. If a bit is a 1 and you have a 1 in the literal value there, then it will toggle to a 0. So this will effectively toggle all of the output values in the places where you put 1s in that literal. So that's a nice way to blink a light on or off. We can also do ANDing, inclusive ORing, and exclusive ORing between the value that we have in W and the value in any special function register. So to do this, you would simply load up the value that you want into W first, and then perform this on the entire register. So the entire register will bitwise be ANDed, ORed, or XORed together. And the result here can be stored into the W register with a comma 0 or back into the special function register itself with a comma 1. We can also complement a register, meaning flip all the 0s to 1s and vice versa. So if you do COMF, the register, you can put the result of that into W. So the example here, COMF tris_B, comma 0, would put the exact opposite of tris_B into the W register. If you did COMF tris_B, comma 1, then that would put the exact opposite back into tris_B. This is another way. It's good for blinking lights on and off, flipping them back and forth, so just complement, complement back. You can also use this to prepare for some mathematical operations. If you're trying to prepare, say, a 2's complement, this would create the 1's complement, and then you could put a 1 in the carry bit to create the 2's complement. So let's go ahead and trace through the value in the W register and in port B after the following commands are executed. You can go ahead and pause the video and try to work through tracing through those on your own. Once you think you have a solution, go ahead and restart the video and we'll explain the results. Okay, so let's go ahead and look at this. Again, we started with a CLRW that puts zeros in W, doesn't change port B. We're moving, in this case, a decimal 10 into W, and so in this case we have 1010, which is binary for decimal 10. Still didn't affect port B. We're doing an exclusive OR with hexadecimal 63. So in this case, our 6 is showing up right here. And so that toggled where the ones were. These were zeros, and we had zeros in our literal value, so that stayed a 0. There were ones in our literal value for the 6, and so those showed up here with the zeros being here. And then we had 0 originally. We had a 0 in our value of the literal, so that showed up down here. And then the 3 is going to be 0, 0, 1, 1. So the zeros allowed this 1 and 0 to be maintained and actually toggled the last two values. So we see that happening. And now we're doing an AND, a literal with W, and in this case we're specifying a binary value. And so in this case we bitwise do this with what we had in W before. So 0 ANDed with 0 gives us 0. 0 ANDed with 1 gives us 0. 0 ANDed with 1 gives us 0. 1 ANDed with 0 gives us 0. 0 ANDed with 1 gives us 0. 1 ANDed with 0. 1 ANDed with 0 still gets 0, and 0 ANDed with 1. In this case, all of our values went to 0. That would set the Z bit. So if we were to look at the status register after this, we would see that the Z bit is set. Again, we still haven't done anything with port B. Now we're going to do an inclusive OR of a literal with W. In this case, we're going to do the inclusive OR with F. And so that's just going to put ones right here in our lower bits. So that's taking this 0F and putting ones and the zeros here together through OR gates, and then zeros and zeros through OR gates still output zeros. Now we're going to move W over to port B. So here's now the value of W put over to port B. And then we're going to complement what's in port B, but we're going to put the results back in W. So port B stays the same, but now we have the exact opposite. All the zeros flip to ones, all the ones flip to zeros, and that is stored into W. So this concludes our portion talking about the logical commands. And so in this lecture series of 3 videos, you have seen introduced to you 32 of the 51 assembly commands. So we have seen quite a few of the different commands that are available on this microcontroller. As we go through in future videos, as we go through looking at some other topic areas, you will see the others as the course unfolds.